Hi there. Today we're going to be looking at the ideal gas law, and the ideal gas law shows the relationship between the four variables that you can measure about a gas. And so if we have a container and it's full of particles of a gas, there's four properties about those particles that we can measure and relate to one another. The first one is that we talked about was pressure. Now remember, these molecules or particles inside this container are in constant movement, and they're constantly bombarding the sides of the container. And so every time they hit the container, they exert a force, and that force is over a little bit of area. And if we take all of these particles and talk about all the forces they're exerting on all this container wall, we're talking about the pressure, pressure per unit area. The second property that we talked about is the volume, and the volume is how much space are these gases filling up. We're not talking about the volume of each individual particle. We're talking about how much volume do these gas particles spread out into. And so volume is the amount of space that the particles are spreading out into, which is usually the volume of the container. The next thing is how many particles are actually in there. And since when we're talking about atoms and molecules, we're talking about incredibly small size particles, we have billions and billions and billions and billions and billions. So we can't just talk about numbers in an absolute sense. So we talk about moles. Remember, mole is just a number. It's 6.02 times 10 to the 23rd, just like a dozen is 12. And if we have 1 mole, then we have 6.02 times 10 to the 23rd particles. If we had 2 moles inside our container, then we would have 2 times 6.02 times 10 to the 23rd. So it is just how many moles are present in the container. And then our fourth property is temperature. And so if these molecules are moving and moving and moving, they have kinetic energy. And that kinetic energy is measured by temperature. The more temperature something has, the more kinetic energy the molecules have, or vice versa. If the molecules all of a sudden stopped, then they would have no kinetic energy, meaning they'd have no temperature. And so that's absolute zero, and is 0 on the Kelvin scale. And as you increase the temperature, if you go up in the Kelvin scale, the molecules are moving faster and faster and faster, more kinetic energy. So what we want to do now is see how are all four of these variables related to one another. Up to this point, we've only talked about laws that involve 2 variables, or at the most 3 variables. But how do all 4 relate to one another? And so to do that, we're going to be looking at what's called the ideal gas law. And if you would like to see the derivation of this law, then you might want to look at the Khan Academy video on the ideal gas law, where Sal Khan actually derives this equation. I'm just going to show you the relationship, but that's a really good video for showing you where this equation comes from. So it turns out that if I take the product of pressure and volume, it's proportional, and that's the mathematical symbol for proportional. It looks kind of like the Starship Enterprise if you've ever seen that on Star Trek. But the product of the pressure and volume is proportional to the product of the moles times the kinetic energy, the temperature. And this is kind of like a proportional relationship that you've seen in math, where y is proportional to x. In other words, as y increases, x will also increase. As the pressure-volume product increases, the mole temperature product will also increase. But proportional means that there's some proportionality constant. And so we can say y is equal to some proportionality constant, m, times x. And m is the slope, and it's telling us by how much x is increasing when y increases, or by how much x decreases when y decreases. So the same thing can be done over here. Pressure times volume is equal to some proportionality constant, and this proportionality constant is so important it gets its own letter, r, more about that in a second, times n times t. So now we get, as the pressure-volume product increases, the mole temperature product increases by some factor r. And this is called the ideal gas law. It's more commonly written with the r and the n swapped, and so I'm going to go ahead and rewrite it with the r and the n swapped. So PV equals n times r times t. And this is the ideal gas law. R, like I said, is so important it has its own letter and name. It's called the universal gas constant. And the universal gas constant, as its name implies, is a constant. So since it's a constant, it's a known value, and so R equals 0.08 0.21 liters atmospheres per mole Kelvin. And those units are crazy. Constants usually have crazy units because they need to cancel out all the units that are in the equation. So liters is a unit of volume, and you'll notice volume is in the equation. Atmospheres is a unit of pressure, and you'll notice pressure is in the equation. Moles is, of course, moles, and so N, moles, is in the equation. And Kelvin is the unit of temperature, which is in the equation temperature. So the ideal gas law is an important relationship that shows how all four variables of a gas are actually related to one another. And so in our next video, we'll talk about how to use the ideal gas law in real applications. So until then, goodbye.